Welcome once again to the group exhibit, Hydrogen Fuel Cells and Batteries at the Hanover Fair 2016. My name's Christine. I'll be your moderator for this discussion. We're talking about power to liquids. My guest here is Dr. Christopher Hebling from the Fraunhofer Institute for Solar Energy Systems. He's the director of the Hydrogen Technologies Division. Please do come sit, join us, join the discussion. If you raise your hand at any time, I'll come around and give you the microphone to ask a question. Drinks are on the house. Please do feel free to join us. But first, please join me in welcoming our guest, Dr. Christopher Hebling.
Thank you, Christine. And thanks for staying with us.
So power to liquids is the subject of this discussion, but your group does more than just that. Maybe you want to start with an overview of what it is your group does.
Yes, I'm with the Fraunhofer Institute for Solar Energy System, which is one out of 67 Fraunhofer institutes in Germany, and we focus, as our name says, on solar energy systems. And system means not only the electricity generation by means of photovoltaics or heat generations by means of solar thermal systems, but also hydrogen as being a part of the upcoming solar or renewable energy system. And I'm heading the division for hydrogen technologies with like 100 scientists, engineers, and students.
And what type of subjects do your students and engineers work on within your group?
Well, we have three departments. One department is focusing on the hydrogen generation by means of PEM, water electrolysis. One department is focusing on the mobility sector, zero-emission mobility by means of hydrogen and fuel cell traction systems, predominantly for cars, car transportation. We've heard about buses before, but also light vehicles such as bicycles and things like that, and scooters, and so whatever is, has the term of mobility, also ships. We focus, that's part of it. And the third department is focusing on the topic what we are talking about today, so which means the catalytic conversion of hydrogen once it's in the energy system and CO2 towards whatever you can do with it, fuels and chemicals.
And your group, the Fraunhofers are all over Germany, but maybe not everyone knows the origins, if it's publicly funded or industry funded. How does that partnership work?
Right. Fraunhofer has a kind of an intermittent role between academic research, such as university and Max Planck Society, and the industry. Our business model is in such a way the state gives us just a small portion of basic funding. In the case of the divisions, like in my case, I get 5% of the revenue I generate with my 100 people from the state, and the rest is what we call earned money in terms of projects where we apply project proposals in different calls. And of course our focus is to work with industry. So the mission of Fraunhofer is to have at least 30% of our revenue generated with bilateral collaboration with industry. So in numbers, my budget is like €7.5 million. We spent this year in like 70 different projects. And the basic funding I get for that is on the order of €450,000 from the state. So the rest I can grow however big I want to be, as long as I can pay my staff. So
you're always looking for industry partnerships, is what you're saying?
Yes, and good people.
Yeah, fair. Okay, so turning to the subject of power to liquids then. So power to gas is maybe a more common subject, but so what is power to liquids?
Yeah, we heard from Mark in the previous talk that we are approaching an energy system which has a lot of hydrogen as part of this renewable energy system, because the hydrogen can be produced from intermittent energy sources like wind and solar. So once we have the hydrogen, of course, it's fair to say that the first market would be the mobility sector, such as buses and cars. But we also have to address other sectors which use energy, such as the chemical sector or the fuels. We know that hydrogen is a perfect fuel for fuel cell buses and cars, but once you approach like ships and aircrafts, for example, so they will never run on batteries or hydrogen with fuel cells, because the power density is not high enough, and also the power of the fuel cells would never be enough for like a large airplane, which means we always will need liquid energy carriers, hydrocarbon energy carriers, and it's also a target of this century to transform liquid energy carriers from fossil bases, fossil feedstocks as we have today, towards synthetic fuels with the same properties, but made out of hydrogen and CO2. And once the hydrogen is green, which comes from PEM electrolyzers, and we have at least 4 companies here at the fair which produce megawatt PEM electrolyzers, and so once we have the green hydrogen just coming out of water and power, and CO2, we have enough flue gas streams from cement industry and all this kind of, and biomass converters. So if we capture the CO2 from those streams and combine it with the hydrogen from electrolyzers, then we have the whole chemical playground is open. So the first fuel would be methanol. So that's what we call a platform molecule, because methanol is needed for all kinds of subsequent sectors, energy sectors, chemical sectors. Methanol, just in numbers, is used in quantities of 80 million tons globally. And 80 million tons are produced. Half of them are produced of coal, the other half of natural gas. So, and if we can substitute consequently those 2 sectors by means of synthetic methanol, then we are approaching a more and more CO2 neutral society. So that's the background, so to speak.
Okay, so if you get your hydrogen from green sources, from electrolyzers powered by green energy, your carbon you get from flue gases, would you choose to co-locate your systems next to a biogas plant, for example, or next to a chemical plant in order to directly use the carbon dioxide? Or
right, that addresses 2 questions. First, the feedstock of CO2, that's one issue, and the second is, where does the power come from? And as we know, in Germany we have this incentive system, and if you use or feed in the power into the grid, then you have to contribute to this incentive system, which adds at the moment 6.2 cents per kilowatt hour if you participate in the public grid, so to speak. If you remove, even if you put in your own power into the grid, and if you remove it later, then you have to pay 6.2 cent per kilowatt hour, which destroys every business case, because the power we're targeting right now is the cheapest power, of course, which you would curtail right now, and so this is the base of the business model, and so you would try to avoid this 6 cent, and you can avoid it if you put your electrolyzer next to the wind power plant, first of all, but then you have to make sure that you also have a permanent source of CO2. So that's and this can be done certainly if your biomass plant is also situated next to the wind power plant. So this is kind of the starting process, because then you don't need to pay for the fee, the grid fees.
Okay, and you've done full system modeling that suggests that's the best approach, is co-locating and creating a full green system.
Yes, we do this life cycle analysis. I mean, our services start from catalyst development, so we have a strong backbone in 25 years of catalyst development. Then we do process development, processes with a given catalyst to a targeted product, which could be methanol, but even could be more. So because methanol, as I said, is a platform molecule which can be processed further, and that's what we do in terms of further processing to OME, that's oxymethylene ether, which is a diesel replacement. You can use it directly in your diesel engine. And the big advantage of these, it's a group, so to speak, OMEs of this group, you can tailor the properties exactly to the application, because you have nothing but CO2, hydrogen, and oxygen, so to speak, and there's no anything else like nitrogen or whatever is in the diesel. All this alkene group, so it's not in there. So you have a highly pure fuel because you synthesize this from your hydrogen and CO2, and then you can tailor the properties exactly to your diesel engine, as an example, but also with DMEs, that's dimethyl ether. So it's a whole group of liquids which can be used in the transportation sector.
Okay, and if you're creating these liquids from the cheapest electricity when you're load smoothing and stabilizing the grid, that it can have a cost-effective argument. So how does that compare to other, so effectively you're storing energy in chemical storage. Do you know how that would compare to other storage options such as batteries or compressed air or pumped water or hydrogen directly?
Right. Yeah, I'm glad you give me one other hour to talk to you about this issue, because it's hard to compare, a liquid fuel to replace, which you need for like ships, for freight ships. But to make it short, with batteries, they make a lot of sense to store electricity like from daytime to the evening, just to shift it for a couple of hours to the evening time to watch TV from the PV power at the daytime once you were working, as an example. That makes total sense. In the megawatt scale, you can start debating if it makes sense, like for a commune, for a region, to have a battery storage as a kind of a storage like a small city, because then the batteries, they scale with capacity. So you have huge installations with, at least with lithium batteries. There are redox flow batteries which make a lot of sense, but they are more on the weak scale energy storage. Hydrogen you can store basically forever, especially in underground caverns, as an example. So therefore, with pumped air, you said pumped air. This is for me, it's pretty much the silliest option, because you just squeeze it underground mechanically and then release it again, and then you have the mechanical energy back. So this is, I think, with hydrogen, it's a much smarter way, because hydrogen, as you know, is very versatile. You can use it directly in fuel cells, and you have tons of fuel cells sitting here around. Then you have heat and power, and the best combined heat and power systems, they have an efficiency of 94%, as to my knowledge. So then you get all your energy back in heat and power. So with other storage options, once again, batteries are absolutely fine, but then it's just you store your electrons for a certain time and bring it back as an electricity. If you want to approach other applications, other sectors, then hydrogen is a way to go, especially if you go for large quantities. And it's not a surprise that a lot of those companies you see here, they address now the 2 to 5 megawatt, but Mark mentioned the 80 to 100 megawatt scale, and there at the latest you are way beyond batteries.
So it's not so much a question of direct competition as different markets almost. So it's tough to compare.
Yeah, it also, I mean, you're asking about business models. This would be another talk. So which fruits are hanging the lowest? And we do this, as I said, this life cycle analysis. I mean, the simplest answer would be synthetic methanol nowhere gives any business case at the moment, because the fossil fuels are so cheap at the moment, so even renewables have a tough times to compete with such cheap natural gas, for example, you know. But we do sensitivity analysis to see which parameters have to change in which direction so that business cases would show up. And the first, I mean, first of all, the price of electricity that plays a major role. You know, is it 4 cents? Is it 0 cents? Or is it 26 as we have it when we just take it out of the grid at the moment? Second, the price of CO2. I mean, it's basically zero at the moment. It's neglectable. If we are serious with the COP21 targets of last year, if we're serious with that, so we have to give CO2 a price tag at a certain time, which could be, I mean, with like 30 euro per ton, then the first business model would show up automatically without any subsidies. You know, if it would go further up to maybe 100 or so over the next decades, you know, then I mean, the whole hall would be full of hydrogen applications. You know, so there are several factors which play into also the scale effects. You know, all those units you see here are handmade basically, so they. People are sitting there manually and building it, you know. If we go really to a market which is approaching like gigawatt as an example, then of course, and Hydrogen Society was announced by Japan recently. They really want to make the difference, and Japan wants, like for the Olympics in 2020, they spent $350 million just to demonstrate the power of hydrogen in the various fields, like buses, and they set up hydrogen stations. They will have all kinds of hydrogen applications. As I said, just for the Olympics, 350 million. So they want to show and that this is the way to go. That's why Toyota is so enthusiastic about their hydrogen strategy and fuel cell cars. And they, in Toyota City, they are just about to build a new factory for the fuel cell cars, which will be CO2 neutral. So they will produce the hydrogen on site, which is used also in the factory. So Japan is very decided. There are other nations which might follow, I assume. But according to your question, with business models, you really have to see the total, first of all, the vision. Where do we want to be in 2050? Minus 80% CO2 reduction, that's the target of the German government. And if we want to follow this path, especially the mobility sector has to jump and make big steps right now, because the mobility sector did not contribute over the last 25 years in CO2 reduction. They even spent a bit more than in 1990, whereas the power sector and like households, all other sectors, agriculture, they all decreased their CO2 footprint and emissions. The mobility is still increasing, so therefore this is the door is wide open for zero emission applications in the fuel cell sectors.
Excellent. Are there any questions from the audience at this time? Okay, then I get to ask mine. So is cost then the largest barrier to commercialization, or is there political or technical challenges that are more of an issue?
Well, it's cost and cost. So.
Just cost. So politically there is will, and the technical know-how is there.
Well, first of all, we're talking about moving targets. I mean, batteries are getting cheaper, and you know, all other competing technologies are getting less expensive as well. I think in terms of durability, we have done over the last decade a great job. All the scientists and engineers which worked on their products can make sure that durability, for example, for electrolyzers, they are like beyond 10,000 hours and things like that. Cold start of fuel cell cars is not an issue anymore. technically speaking, we are on the right track, and we have solved, I would say, most of the problems. But it's always, I mean, you can solve each problem if the amount of money which is allowed is unlimited, you know. So therefore, you have to always kind of balance, you know, the effort you have for a product and the outcome of the product, you know. So therefore, we have to scale it down, which is happening right now. So the amount of platinum went down by a factor of 10 over the last 15 years. You know, the first like B-class fuel cell cars, it was A-class from Daimler. They had a platinum loading of 220, I think, milligrams per square centimeters. Now we're on the order of 25, 28, so nearly a factor of 10. This is the result of research and engineering, and still having a higher power density as it was at the time. But this is all addressing the cost issue. So, and once we come into scale effects, this will trickle down immediately.
Okay, well, we're all waiting somewhat patiently for the commercialization. Unfortunately, that's all the time we have for this talk. Please do stick around for our next talk, which is product news from H2 Logic with Jacob Krogsgaard, who is the CEO. But first, please join me in thanking Christopher Hebling for this very interesting discussion.
Thank you, Christine. Thanks for joining. Thanks.